Water is one of the most critical resources on our planet. Accurately predicting stream flow is essential for water resource management, flood prevention, and environmental conservation. In this project, we aim to predict the next 3 days of stream flow for 4 rivers in Santa Clara, California, using sensor data collected every 15 minutes, requiring a 288-step forecast. Our model uses as input a time series of past stream flow values and one or more associated time series, such as rainfall or stream flow from nearby streams. In this example, we can see real data from the Ross Creek in Santa Clara, California. The upper series shows the stream flow and the bottom one the rainfall values. We can see that the rise in stream flow is usually preceded by rainfall. In other words, these two sequences contain rich temporal relationships that are slightly misaligned in time. Another notable characteristic of these two sequences is observed in winter, which corresponds to California's rainy season. During this period, stream flow increases in sharp peaks, contrasting with the near-zero values during dry periods. Based on our observations, transformers struggle with time series data that contain infrequent yet crucial extreme values. In a traditional transformer model, positional embedding, or PE, is used to order values in a sequence. Each position is assigned a value based on a unique combination of sine and cosine functions at different frequencies. As an example, we show a 6-dimensional positional encoding that uses a gamma distribution to model sudden peak rises due to rainfall. The cyan line represents the original stream flow, while the red dashed line shows the stream flow after applying position embedding. As seen, position embedding introduces noise, causing key inflection points to shift and become exaggerated, potentially distorting the true temporal dependencies. We claim that informative multivariate signals can make position embedding unnecessary. Instead, our model uses cross-variable patches to naturally encode temporal dependencies more effectively. The PF-former framework we proposed is a transformer-based variant optimized for multivariate time series forecasting. It replaces the encoder's positional encoding layer with enhanced feature-based embedding, or EFE, to capture complex intervariable relationships. For an input sequence of length t, taking the first time point as an example, EFE combines the predicted sequence value at this time point, corresponding values with auxiliary sequences, and S preceding values from each of these auxiliary sequences. The sequence is then transformed through a dense layer coupled with a nonlinear activation function. These elements are concatenated to form a multispatial subsequence unique to that time period. Adjacent inputs naturally have smaller distances when concatenated. In other words, they inherently preserve positional relationships. We use the hyperparameter S to control the concatenation length, allowing our model to adapt to more complex and longer sequences as necessary. In our experiments, we found PF-former outperforms both the traditional transformer model and one without positional embedding, as well as many other state-of-the-art approaches in terms of root mean square error on 3-day-ahead rolling predictions across 4 different streams. Additional results can be found in our paper. We will now share some example predictions using PF-former from 2 Santa Clara County waterways. The first animation shows streamflow prediction for the Upper Penitentia Creek, which is prone to flooding during times with unusual heavy rain. The graph displays predictions between December 8, 2021 and January 15, 2022, a period which included heavy rains. Every 4 hours, we predict the stream's flow rate in cubic feet per second for the following 3 days, shown here by the red prediction line. While most of the time the creek is dry, unexpected rain can cause the flow rate to increase drastically. Our model is able to stay ahead of these predictions, as shown by the green ground truth line that follows the red prediction line almost perfectly, in part with help from the rain gauge data shown in gray. We have slowed down the animation during the heavy rain period to allow closer inspection of the data. The second animation shows streamflow prediction for the San Francisquito Creek, another creek prone to flooding that has had considerable flood protection features added since 2016. We see that PF-former is able to accurately predict ups and downs in streamflow along several extreme weather event periods. PF-former is one of several streamflow and reservoir water level prediction models we have developed in recent years. Some of our hydrologic prediction models have been integrated into FlowView, a web-based monitoring platform that enables Valley Water to intuitively visualize predictions. FlowView automatically trains models based on user-selected parameters and generates 3-day-ahead forecasts, updating them every 4 hours. By providing timely and data-driven insights, FlowView supports Valley Water in making informed decisions for water resource management and planning. We would like to extend our gratitude to several of our partners in this project. First of all, Valley Water made the project possible by providing the data used for this research. VDURA is designing a parallel storage solution for the Santa Clara University High Performance Computing Center that will allow us to efficiently process large-scale data. Finally, we would like to thank Supermicro and NVIDIA for providing our lab with a high-performance GPU server equipped with NVIDIA HGX A100 8-way GPUs, which made the training of these models possible. These contributions have been instrumental in advancing this research and driving innovation in streamflow forecasting. This project is led by me, Professor David C. Anastasiou from the Department of Computer Science and Engineering at Santa Clara University School of Engineering, and is being developed by my PhD student Yanhong Li. Our paper, PF-Former, a position-free transformer variant for extreme adaptive multivariate time series forecasting, will be presented at the 29th Pacific Asia Conference on Knowledge Discovering and Data Mining, PAKDD, in Sydney, Australia this June. Thank you for watching our presentation.